So let's go through, yes,
I just have one other thing, even though it's aimed at an undergraduate audience, I think if it's not your specialization, I think it'd be something that's found to be interesting even for people with your.
right. I always like bringing people over to the dark side. So, so I'm gonna go through some theorems. This is mostly kind of, looking at properties of the integer, although in some cases I'll talk about it in terms of PID, where it's more general here. This one's definitely kind of, this one can be generalized as well. Classical theorem. Here, Clay. Let M and let's say R be relatively prime. And then there are infinitely many primes. In sequence R plus M N. Right. This is so for example, if you have, I don't know, 2 and 3, and so you look at 2 plus any multiple of 3, as you go through that sequence, you will find infinite primes. This can be generalized some in more general settings, Chebyshev density theorem, where we look at ideal classes later. Let me give you a definition here. I'm going to prove this right now. Let R be a domain, so I'm going to do this in terms of more general. And let's just make this easier. Let's forget about 0 for a minute. The greatest common divisor GCD evey. So when you see that notation, that I just mean greatest common divisor of the 2 elements A and B is an element P and R. By the way, what do you suppose we mean by greatest common divisor?
You know, the divisor divides.
Okay, well, so if it's going to be a greatest common divisor, it's going to be a common divisor. So let's do that first, such that D divides A and D divides B. It's common divisor. But what do we mean by greatest? It's very natural to think of biggest, in the integer size wise. The greatest here means the divisibility thing. And if there exists D prime in R such that D prime divides A and D prime divides B, then D prime how many of you have seen that? Okay. Let me break this up into 2 parts. Well, that's 1, 2. The least common multiple LCM of 2 elements is let me say, if it exists. I may have verbally said that, I meant to write that down. The greatest common divisor of two things does not necessarily have to exist. It will exist in certain types of domains. But there's some domains where I might pick out two elements that accidentally don't have the greatest common divisor. The least common multiple is an element M and R such that, well, again, it's got to be a multiple such that A divides M and B divides M. So it's a common multiple. And if M prime is another common multiple, then M divides M prime. So that's what we mean by least. It divides every other common multiple. By the way, which of these two concepts is stronger?
Greatest common divisor.
It's actually least common multiple. So maybe I want to work through that and make sure that I'm right about this, but as I recall, if you have two elements that have a least common multiple, they have the greatest common divisor. The converse is not necessarily true. You have two elements that have a greatest common divisor, they don't necessarily have a least common multiple. I've always thought that's interesting because one would think that these two properties are equivalent, but they're actually not equivalent. Well, you would think that they would have equal strength. I'll put it to you that way. So here's a statement here. Theorem, if 316, if R is a PID and A, D, and R, let's say they're non-zero again, then exists and there exists X, Y, and R such that this is actually an incredibly important property of PID. That is that not only does any pair of non-zero elements have the greatest common divisor, but you can also express that greatest common divisor as a linear combination. Let me do a quick proof of this. Consider the ideal AB. Just take the two elements, generate their ideal. Would it be too much of a spoiler if this is a PID, right? So this ideal must be singly generated. Would it be too much of a spoiler if I did this? Gee, I wonder what the greatest common divisor of AB is, right? Notice I'm going to show you directly that this works. Notice D divides A and D divides B. Why is that? Well, because both A and B are in this ideal, so it must be a multiple of that. So okie dokie so far. Got that. It's D is a common divisor. Now, also note that there exists X, Y, and R such that D equals AX plus BY. But that's the other containment of the ideal, right? That is, this thing must be a linear combination of A and B, right? So now we've got this, and this gives the greatest common divisor. So if D prime divides A and D prime divides B, that means D prime divides the right hand side of this equation, therefore D prime divides. Okay, so what we've shown is that a principal ideal domain is a GCD domain. I haven't defined that, but I bet you can guess what a GCD domain is. Any pair of elements has a GCD. Can anybody name a more general type of GCD domain? And don't say GCD domain because I couldn't argue with that very well. But something something more general would be.
Bezout.
What's that?
A Bezout domain.
Yes, that works, but let's not. Let's not Lance Armstrong that thing.
UFD.
How about a UFD, right? So a UFD is a GCD domain. Now, let me ask you this, and actually, Adam, your example is very good, but I'm steering in this direction because I want to ask you, how can, if you're in a UFD, how do you suppose that you could select the greatest common divisor? Can you name an algorithm for just kind of what you might do to figure out what the greatest common divisor, two elements is? That's essentially it. In fact, since this is not zero, there's only finitely many primes dividing A and finitely many primes dividing B, right? And finitely many could also include zero if A or B is a unit, right? So let's collect all the primes that divide A and B, and we'll call them P's. Let A equal P1, M1, P2, M2, PK, MK, and B equal P1, M1, P2, N2, up to PK, NK. So I'm using the same, let me point out that each MI, NI is greater than or equal to zero. So for example, if A is one, all the M's are zero, right? And this way I can get all the primes together. So can somebody tell me how I just cherry pick this out?
And find common P1s, and PIs, and raise them to the least of the NIs.
Just go through and pick the minimum. Anybody want to guess what the least common multiple is? The max. This is easily verifiable, but I'll bring this up to contrast this with theorem 316. Does everybody kind of follow that that's how you would do the GCD? And if you just kind of sit down and write it out, it's pretty easy to see that D is a common divisor and it's as big as possible. The greatest for the divisor and the least for the multiple basically follow from the fact this is UFD. You get unique decomposition into primes. However, can this be expressed as a linear combination of these? Not in general. And let me give you a concrete example of this. And this is about the easiest example I can think of. Let R be some field So I think you all will go with me on this, although we're gonna talk about it later, that this is a unique factorization domain. Because you all nodded very vigorously last time that if you have polynomial ring over UFD, it's UFD. So this one's UFD, right? That's not too hard to swallow, I think. Consider the two polynomial variables x and y. These are both primes, right? You can see that very readily because when you mod R by the ideal generated by x, you get Fy, which is an integral domain. Both of these are primes, right? Well, it should be x to the sum power, y to the sum power, and it's got to be 0, right? Because the min on both is 0. The greatest common divisor of this is 1, right? But there's no way you're expressing 1 as a linear combination. Just plug in. This is basically plugging in x and y as 0, gives a homomorphism from R to the field F, and you get 1 equals 0. That's a pretty blatant contradiction right there. My contradictions are almost never so clear. Okay, questions on that? All right.
If you have a UFD where you can write the greatest common divisor as a linear combination of equal elements, is that then a PID?
So what you have, I think with your question, so the question is, if you have a UFD and you also throw in the extra property that any two non-zero elements, their GCD is expressible as linear combination. That means that any two generated ideal is principal, which means it's a Bezout domain, which means it's a Bezout domain in the UFD. It has to be a PID. So yes.
What if you have like a non-notarian UFD?
Yes, you can certainly have a non-notarial UFD.
Yeah. Is it still the case that if you assume that all the finitely generated ideals are principal, then it's because like going with what he was asking, right?
Okay, so what you have is, sorry, this is a little careful. So suppose you have a UFD. Or two. Every pair of element of the GCD of AB is a linear combination. Those are the two properties you want right at. So suppose you have this. Well, the second property 2 every finitely generated ideal is principal. Now, what property 2 actually basically says is every two generated ideals principal, right? And then you can go by induction, right? So So if you have X, Y, Z, this is X, Y, Z. Right, whatever this side, but this is singly generated, which is DZ, which is alpha, right? And just keep going by inertia, right? So R is now a UFD. This is an interval domain that has this property is often referred to as a basic domain. It means that it's not necessarily Noetherian, but any ideal that is finitely generated must be principal. So it's sort of a non-Noetherian version of the PID. So R is a UFD. So this is a UFD where any finitely generated ideal so I claim that so I claim that actually this is a principal ideal domain. So how are we gonna show this?
It's enough to show it's Noetherian, right?
Mm-hmm. Yeah, it's enough to show us a theory. There's actually another way that we can do it. Another way. It's enough. Show any non-zero prime ideal is maximum. Remember, earlier in class, not today, but earlier this semester, R is a PID if and only if R is a UFD. And okay, so how are we going to do that? Seriously, probably present time for that. We're gonna do that.
Well, suppose you have to change prime ideals, find persons.
Okay. What do we know about this prime ideal?
It's either principal or infinitely generated.
And it contains a principal.
So, since R is a UFD, there exists a prime element. So what we have. I smell blood and water now. No, I shouldn't put this here. This could be equal. In fact, what we want to do is show these are. Any ideas how to do that?
If we added any other elements to P.
Right, so here's an action photo of what's going on here. Here's P. Here's the ideal driven by X. Suppose that this containment is strict. Then there exists Y, P, and X, right? So here. Now, well. Let's see what's going on here.
P is the GCD of X.
Now consider. This ideal is Y. It's generated by D. And there's only two choices for the GCD, X and Y. What are they?
One is, or
That's right.
Yeah.
If GCD, because remember, X is a prime, right? So it's only factor, it's a non-zero prime, so it's irreducible. Its only factors are essentially itself and one. And this is a contradiction. Do I agree with you? So if the GCD of X and Y is X, then done. If GCD of X and Y equals one, we'll see now by Adam's hypothesis here, that's expressible as a linear combination of X and Y. Bayesian property, if you will. And Adam, start calling you Adam Bayesian, I guess. There exists R, S, and R such that Rx plus Sy equals 1. Agree? And this is a problem too, because this is in P. It's a contradiction. So P is equal to X, and every non-zero prime is present. So R is a yeah, well, we've done this several ways. We've proved that every non-zero prime is principal. That works. We've also, if you want to go old school, because this last statement really depends on your doing homework. If you want to go old school, basically we've shown this every non-zero prime is maximal, and that goes back to this one right here. Okay, that was a fun aside. This is the greatest thing about a class like this, is we can just go do this crazy stuff and not have to worry. Okay, any questions? Well, that was fun. Keep them coming. Here's one that I bet you all know. What are the a domain and Yeah, I can. Yeah, actually. I'm. Or, so I can say this for everyone. Yeah. The RB principal ideal domain and suppose AD, you can do this in the GCP domain too. If D equals and L I know what this one is. This is something you almost always get undergraduates to prove in like a first number theory course. And actually I don't think that this is one of these problems that I always give when I teach like a 3190 or something like that. And every time I put on homework, I have to make sure that I sit down and work through it again. It's like, it's a little bit obnoxious. If you don't want to do prime factorizations, this is A times B. All right. Another way to get AB is to take the greatest common divisor times the least common multiple. Try to prove this. I mean, it's not terribly difficult. Try to prove this without assuming that the ring is a UFD. That's more fun because of the prime factorizations. It makes it a little bit too easy. Okay. All right. So here's another big thing that comes out of looking at the rational integers. And I'm going to state this. Yeah, I state this in terms of integers. Need to make sure the Chinese remainder theorem shows up instead of just CRT. I don't want the Sands coming in here and flogging me to death. But the Chinese remainder theorem and Mau's little theorem. So I'll start off with the Chinese remainder theorem. Let M equal MP with MIMJ. By the way, you can interpret this many ways. This is kind of a standard notation when you're doing this. This does look like the ideal generated by this, and you can mean it that way, is equal to 1. So in other words, the greatest common divisor of every MIMJ is 1. If I and J are different, of course. So this is just a relatively prime factorization of whatever M happens to be. Then the system of equations X is equivalent to B1 mod M1, X is equivalent to B2 mod M2, bring it on down, X is equivalent to BT mod MT, as a solution. Mod M, mod the product of all these, as a unique solution mod M, let's say any two solutions that you get by pulling back the integers vary by multiple n. So for example, I'm gonna what is meant by this. And actually, we're gonna see some places where we actually apply for the, apply this. Let's let M equal, 180. Now, suppose I want to solve. And I'm gonna factor it down this way. Yeah, give me three numbers. Less than 4, less than 9, less than 5 to make my life easier. Okay. So suppose that for whatever reason, I want these three conditions to hold. And we're actually going to see some applications where, I mean, I'm not just making up stuff because it's so fun to do. This actually can be practical. So from a practical point of view, how do we find the solution to this? This theorem over here tells us that this should have a unique solution mod 180. Right? Well, the first thing I know, so I'm going to vary. Don't go tell Lee or anybody that this is the way I'm computing things because he would probably laugh at me. But I'm just going to kind of go through this. I'm not claiming that it's very efficient. Right. So I'm going to sweep it out this way. I'm going to try to solve these two first. Right. So whatever I get must be equivalent to 6 mod 9. So that forces these values, right? Do you see any that are also equivalent to 3 mod 4? Actually, my first instance I get is 15. Do I agree with you? Now, what I have is I've got this solution here. X must be equivalent to 15 mod 36. Right? This is putting back the Chinese remainder theorem piece by piece, right? My 15 works here, my 15 works. Right? And so that should take care of every 36 steps. This has made my life a little bit easier. So now I don't have to go through but maybe about 5 steps for this. So X file X must be 15 or 51 or 87 or 123 or 159. And certainly I'm going to go past 180 if I do that. And these all work, of course, for the first two. So all I need is for it to be equivalent to 2 mod 5. And so 87. So my solution, big picture solution, these are the candidates. This is actually kind of quick. I mean, you wouldn't want to go through this piece by piece. Has anybody heard the sort of the, I don't know if I'm quoting you correct history or not. Unfortunately, I'm not in history, and doubly fortunate I'm not in history in West Virginia. But what's has anybody heard the story of how they did the Chinese Remainder Theorem? Yeah, the story I always heard is the Chinese wanted to count how many soldiers maybe they had left over after a big army. So they trained them to arrange themselves in blocks, right? Like squares or whatever. And they would do this a couple of ways and see how many people were left over each time. and they would basically solve these congruences. And so this is very quick, you can quickly figure out, you know, and of course, you'd have to know some kind of big picture thing. I mean, you'd know that, yeah, the number of people that I have left over after the battle is between 0 and 20,000. It's not gonna be 2 million. And once you've got that parameter as well, you can use this and quickly figure it out. I mean, we narrowed this down out of 180 equivalence clauses pretty quickly, didn't we? Right? Okay. Let's see here. So this amendment here will give you another statement on the Chinese Remainder Theorem, among other things. Lemma went in. Went in 0, and consider Z mod n. I'll use those notations back and forth, at least for now. Number 1, Zn is a finite range with n elements. This is no surprise to any of you. Zn is a field if and only if n is actually, let me see here. N is bigger than 1. Yeah, I do. I'm gonna change this. If n is 1, this is degenerate, right? This is my problem here. Z mod 1 is Z mod Z, which is the 0 range. Here. Z is a field if and only if n is prime. Here's a statement that is more generally true, and I might get you to sort this out. In Zn, every element is, anybody know what I'm going to say? I think those kind of questions, I'll do it anyway. What am I thinking?
Either a unit or a 0 divisor.
That's exactly right. This is kind of weird for a finite ring. Every element in a finite ring is either a unit or it's a 0 divisor. This is wildly untrue for rings that are not. Like if you look at the integers, right? The only units are plus or minus 1. The only 0 divisor is 0. Everything else is neither a unit nor is a 0 divisor. A unit or if we can factor in, right, each pi prime and each ai greater than or equal to 1, I don't want any missing ones here, then Z mod n is isomorphic to Z mod P1 to the A1, Z mod P2 A2, Z mod PN AN. You can call this direct product or direct sum because it's only finite in many of them. This is an equivalent statement of Chinese Remainder Theorem. And in fact, all you really need to do is all you really need to do is break this up into relatively prime pieces. They don't have to be the separate prime powers. Okay. So let me look at some Thanks, yeah. Okay, how smart I am. I need to get two solutions that way off the bat. X is plus or minus one and Y is.
Oh, you're so smart.
Here's the $64,000 question. There we go. Actually, there are infinitely many numbers. I challenge you to find one of them. How do we find solutions to such things? How do we know when it does or doesn't? This one's a type of equation that we're going to see later. Bell's equation. This actually has infinitely many solutions. I'm not going to do my reveal yet. But here's another question. How many solutions does that have? Now I can't do my lame brain solution anymore, right? Because plus or minus one and zero doesn't work here. This one has no. There are no two integers, and I should have said the integers, and I apologize for that. There are no two integers x and y that balance that equation. Okay, I mean, how in the world do you show such a thing, right? It seems like a very frustrating and daunting task because there's infinitely many things to check, right? Well, this is part of the power of modular arithmetic. Suppose this has a solution. So you have x squared minus 10y squared is equal to. So you can find some integers that do this for you. Reduce this mod 5. Why mod 5? Well, I'm a lazy man and I want to get rid of that 10. So if I'm going to reduce mod of prime, it's either going to be a 5 or a 2. And 2 doesn't seem very useful because that will be x squared is equivalent to 0 mod 2, which has plenty of solutions. However, now we're looking at solutions to this. And this is much easier to check because there's only finitely many things. This equation is equivalent to x squared is equivalent to 2 mod 5. And at the risk of being, I mean, all you have to do is make a table here. X squared, 0, 1, 2, 3, 4. 0, 1, 4, 4, 1. No solution. No solution is, and there's only finitely many things to check. That is super cool. Because the existence of the solution here in the integers would give one here. So no solution here means no integer solutions to x squared minus 2y squared plus 2. When I first, somebody pointed that out to me when I was in undergraduate school, I just thought that was fantastic because it reduces checking infinitely many things to checking this equation where you've only got finitely many things to plug in the first place. Let me give you another kind of teaser question, and then that'll be it for today. So here's another question that we will explore from various aspects as we go forward. Can be expressed as some two squares. So P can be written in this. Which primes can be written? in this? And if you can answer that, which numbers? Big ones. Ooh, I bet no negative ones, but besides that, who knows? Okay, any questions? Any questions? Is that a question or a stretch? Oh, yes,
Isn't this like also useful like for PIs?
yes, that's right, because actually the p-adics are a big field. For solving equations in the p-adics, in many cases, you can reduce them to modular. Which is kind of cool. Good question. Others? We will see you folks next time.